Sanjay Chaudhary is a senior director at NVIDIA with a background in both traditional computational methods as well as AI in science and engineering. He leads the engineering efforts on SIMNET. Oliver Henning is a senior software engineer at NVIDIA with a background in machine learning and scientific computing. Oliver's interests are in accelerating traditional simulation workflows using machine learning and is a lead developer of SIMNET. SIMNET is an AI toolkit for multiphysics simulation. More broadly, it is a neural network solver for ordinary and partial differential equations. Its primary applications so far have been in the area of engineering physics, although it can just as well be applied to other areas like computational biology or chemistry, high energy physics, finance, etc. The ODEs and the PDEs can be represented in either a strong or differential form or a weak or variational form, as many types of singularities, discontinuities, and gradients can be treated more naturally using the latter representation. The network is physics-driven and in that sense does not need any training data to solve the problem. SIMNET has the ability to model simple shapes using its constructive solid geometry module or complex shapes using its sign distance function library for STL representation of the geometry. Several network architectures and features have been developed or modified in order to model the physical behavior. Multiple configurations can be simultaneously trained using the parameterization of geometry and physics. Performance has been optimized for single as well as multiple GPUs and nodes. And last but not the least, several APIs exist for researchers to implement their own functionality while making use of the computational machinery existing in SIMNET. There are four major areas under continuous development in SIMNET. The first is performance. Here the emphasis is solving larger problems faster with several features like the accelerated linear algebra, automatic mixed precision, and TensorFlow 32 support for a single GPU performance, as well as parallelized implementation for multiple GPUs and nodes. The next is an ever-expanding breadth and depth of different physics types used to model real-world applications. The third is the parameterization of both geometries and physics to solve multiple configurations. And finally, extendability, customization, and ease of use features for researchers to adopt the SIMNET platform. We hope to serve the science and engineering ecosystem by developing and maintaining this platform that can benefit the entire community. To that end, we collaborate with several organizations where if the users wish to include their work in our platform, then they can contact us directly and do so freely. The IP in this case still belongs to the developers, but they can share their work with others who are also using our platform. One can see from this chart that there are four major application areas for SIMNET: data simulation and inverse problems, real-time simulations, design space exploration and optimization, and improved physics and predictions. On the x-axis, the left column shows data simulation and inverse methods for real-time applications where there is no traditional solver available. The right column shows design optimization applications or problems where fine details may need modeling. Here, traditional solvers exist, but the computational performance is a major bottleneck. Similarly, on the y-axis, the bottom row lists the class of problems that can be solved purely using physics with initial and boundary conditions, while the top row needs some measured data along with the physics. Typically, this data would come from imaging studies or sensors in IoT applications. Each of these application areas has been addressed using SIMNET and will be discussed in the next few slides. The first application area is that of inverse and data simulation problems. Here, the concept of solving an inverse problem is demonstrated using a simple example of conjugate heat transfer. The heat flow in the solid is modeled using the conduction equations, while the heat flow in the fluid includes the convective term as well. Temperatures and heat fluxes at the interface of the solid and fluid media are continuous. Given the data for fluid flow velocities and temperature distribution, coefficients of the multiphysics PDEs are calculated and compared with an open source CFD solver, OpenFOAM. As it can be seen from the results, the kinematic viscosity and thermal diffusivity coefficients found using SIMNET agree very well with the open foam solution. Next, we consider a data simulation problem involving medical imaging of an intracranial aneurysm. A complete background and description of the problem can be found in the SIMNET video on YouTube as referenced by the URL on the screen. The blood flow can be seen using 4D MRI or CT scan, but there is no information on flow velocities and pressures in these scans. A quantitative evaluation of such physical variables is essential for estimation of wall shear stresses that induce cyclic loading, which can lead to fatigue failures in tissues. Here, SIMNET imports a real patient's blood vessel model using an STL geometry to create the point cloud necessary for evaluating these variables in the domain, as well as time distance functions and its derivatives needed for modeling. SIMNET results for velocities and pressures are then compared with open foam, which is a finite volume-based solver, as well as Nectar++, a spectral element-based solver. We refrain calling the solver results as ground truth, since the results can and do vary among various solvers due to the numerical schemes and discretizations used. A good agreement can be seen with both of the solvers, although SIMNET results compare better in the critical high stress area with Nectar++, which uses higher order scheme compared to the lower order scheme used by OpenFOAM. Besides fluids and heat transfer, various other physics types, namely acoustics, solids, and electromagnetics are also implemented in SIMNET. A 2D wave equation implementation with a single Ricker wavelet source at the middle is shown here. Both constant and layered velocity models are evaluated, and the results compared with a finite difference-based framework, DeVito. SIMNET results are found to be in good comparison for both the constant and layered velocity models. For the layered velocity model, not only do the SIMNET results compare well with DeVito solution at times 350 and 750 milliseconds, but also they do not show the reflection found in DeVito results, which are unphysical and inconsistent with the imposed boundary conditions. The next example is courtesy Professor Felipe Viana at University of Central Florida, where he and his research group used NVIDIA SIMNET in building a digital twin of an aircraft cabin. Fatigue crack growth monitoring is critical in aircraft panels. However, one cannot use finite element-based models for prognosis due to the high computational cost. Also, in large fleet of assets, there are serious challenges regarding boundary conditions, operating points, and load paths that can make the stress range less accurate than desirable. It is also challenging to get the data since the output in terms of damage quantification is not available other than visual inspection. The pure physics-based model assumes the local geometry correction factor to be 1.122, while in reality it's dependent on the crack length. Flight data is assumed to be known, and the hoop stresses that govern the fatigue crack growth depend on the cabin pressure differential, which is a function of cruise altitude. A hybrid model with physics and data-driven kernels is then created where SIMNET computes the stress field around the window as a function of pressure differential, which is then used in an RNN to perform the damage accumulation. A comprehensive summary of the study can be found at the PHM Society website referenced by the URL. The final example is a multi-physics simulation of an NVIDIA DGX A100 NV switch heatsink. To date, the published literature on physics-informed neural networks has been able to demonstrate the forward solution of only very simple and academic problems when the training data is not used. The gradients, singularities, and discontinuities introduced by complex geometries of physics make the forward solution of real-world problems without training data extraordinarily challenging. In the heatsink design, the objective is to minimize the peak temperature at the source while satisfying the maximum pressure drop constraint. This is necessary to meet the operating temperature requirements of the heat source on which the heat sink is mounted for cooling. A forward solution without any training data of a parameterized complex geometry with turbulent fluid flow between the thinly spaced fins makes this problem very, very challenging for the neural networks. Comparison of SIMNET results for the pressure and velocity contours, as well as pressure drop and minimum temperature at the heat source, shows a good agreement with both OpenFOAM as well as the commercial electronic cooling software. SIMNET trains on a parameterized geometry with multiple design variables in a single training run, thereby significantly accelerating design space exploration. In contrast, traditional solvers are limited to a single geometry simulation. Once the training is complete, several geometry, material, or physical parameter combinations can be evaluated using inference as post-processing step without solving the forward problem again. Such throughput enables more efficient design space exploration tasks for complex systems in science and engineering. The neural network in this example consists of 10 variables with min, max, and median values in the range of these parameters. The OpenFOAM and commercial solver runs are on 12 CPU cores, dual 3.4 GHz Intel Xeon Gold, and SIMNET runs on 8 V100 GPUs in the DGX-1. It can be seen that SIMNET can solve the problem faster than the traditional solver by several orders of magnitude. And finally, a word on performance. SIMNET performance has been optimized for single GPU as well as multiple GPUs and nodes. Single GPU optimizations consist of linear accelerated algebra, automatic mixed precision, as well as TensorFlow 32 precision. The chart at the bottom shows a single A100 GPU speedup over a V100 GPU. Using an FP32 precision, the A100 is about 1.5 times faster than the V100, but the speedup is over 3 when using TF32 precision. For parallel runs, both strong as well as weak scaling have been optimized. The weak scaling consists of accommodating larger workload, that is more points and larger batch sizes for increasing number of GPUs. As shown on the top left and center plots, the number of points increase linearly, while the time per iteration is nearly constant with increasing number of GPUs. The strong scaling consists of achieving the scalability for a constant workload by increasing the number of GPUs.
All right, so SIMNET is designed to be a general purpose neural network differential equation solver. So what I'm going to talk about is some of the details behind what a neural network solver is. This is oftentimes referred to as physics-informed neural networks. And after that, I'm going to go over some of the key features of SIMNET that we hope will get people interested in it. And so I'm going to talk about the methodology of neural network solver in this very simple example problem of solving this differential equation. So we have this differential equation we're trying to solve, and we have these two boundaries. And so what we're going to do is we're going to construct a deep multi-layer perceptron neural network that's going to map this value x, this single value x, to a value u. And what this neural network is going to do is it's actually going to represent, we're going to train this neural network so that it represents the solution to this differential equation. We're also going to construct this neural network with activation functions like tanh and swish so that the neural network is continuously differentiable. And I'll show why in the next slide that we need that. All right, so how are we going to solve this differential equation with our neural network? So what we're going to do is we're going to construct a loss function that encompasses the equation we're trying to solve and the boundary conditions. And so in this top equation, what we do is we construct a loss function for how well the neural network is satisfying the boundary conditions. And then this second equation is how well the neural network is satisfying the equation. And then we're basically going to sample points randomly between 0 and 1 to compute this loss. We're going to add these losses together, and we're going to minimize this loss as much as possible. And if the neural network has minimized this loss sufficiently, the neural network itself will be our solution to the differential equation. And then I'll note that we can compute these derivatives that are in this equation and the second order derivatives using automatic differentiation that's available in most neural network libraries today. All right, and then so this is just a very simple example. If we set f to be, if we set the function f to be just 1, then we can use our neural network solver, and it solves it very well for this very simple problem. Okay, so one difference we have in SIMNET in comparison to a lot of the literature on physics-informed neural networks or neural network solvers is we write the losses as integrals that we're approximating. So if we rewrite this residual loss, we're going to write it as an integral from 0 to 1. And then you can see that we get that same loss function out if we just approximate this integral with Monte Carlo integration. You can see here. There's some differences. This will scale the losses proportional to the area. This is actually kind of nice because it keeps things consistent across different problems and things like that. It also allows us to compute these integrals more efficiently with things like quasi-Monte Carlo sampling or sampling in certain regions with a higher frequency and things like that. But I bring this up because for the rest of the slides, I'll be showing this integral and the losses. All right. So one of the key benefits of a neural network solver is being able to solve parameterized differential equations. And so I'm going to go over a really simple example of this with our previous example. So we're going to have the same differential equation we're trying to solve, but now we've parameterized the right boundary condition with this value L. And we want to know the solution to this differential equation where we're varying this right boundary between 1 and 2. And so how we're going to do this is we're going to train a neural network. And before the neural network was taking in that single value x and mapping it to u, now it's going to take in 2 values, x and L, and then it's going to map it onto u. And then what we're going to do is we're going to construct our loss functions again, but we are going to vary our L as well. We're going to train on L's drawn from this parameter space. So we construct our residual loss function here. We construct our boundary condition loss here, and you notice that the right boundary condition is now moving. And we're going to optimize these losses and then solve this parameterized differential equation. So this is the solution that our neural network solver gives for different L values. So if we evaluate the neural network with a specific L value, this is the solution it gives for u, and you can see how the this right boundary is varying between 1 and 2 for the different L values. So while this is a really simple example problem to illustrate how a neural network solver can solve parameterized problems, you can start to imagine how this can be a really powerful tool for a lot of different problems. You can solve parameterized ordinary differential equations, or in a lot of the examples that we have in our user guide, we're solving parameterized heat sinks, where we're varying the heat sink geometry in some ways, or the inlet speed of the channel and things like that. So we can also solve inverse problems with the neural network solver. And so I'm going to go through an example of this. So suppose we have that same problem before, but now what we have is we have 100 random points between 0 and 1 where we know the true solution for u. So we know u true at 100 random points, and we want to determine the function f that is causing this solution to our differential equation. So what we can do is we can train a neural network unet like before, and we can also add in another neural network fnet, and fnet is going to approximate this function that we're trying to find out. We're trying to invert out this function. So like before, we're going to set up this loss function for the residual. and now F is coming from our FNet. And then what we're going to do is we're also going to construct this loss function for how well our network is satisfying, is matching up with these 100 ground truth data points that we have. So we optimize our neural network on this loss function, and then given the U true points, the 100 true points coming from this function on top, we know that the solution, the true solution for F should be this function x plus sine 4 pi x. And so we can see how well our neural network solver is able to invert out this function F. And so this plot on the left shows this, comparing the true to the inverted out solution FNet. It does reasonably well. And then on the right, we can see how well our neural network UNet is matching up with the 100 ground truth points U true. So I just went over some of the basics behind a neural network solver and physics-informed neural networks. And so what I'm going to do now is talk about some of the key features of SIMNET that we hope get users interested in trying it out. So SIMNET is designed to be a general purpose differential equation solver. And so from a user's perspective, it's similar to a lot of other differential equation solvers that are out there. So we have tools to define your domain or geometry in different ways, and define your equations and boundary conditions that you're trying to solve for. SIMNET also has a model zoo of different neural network architectures that you can try out from that are in the literature right now. We have some tools to visualize the results and monitor the convergence. We use TensorFlow, and you can visualize the results while training using TensorBoard. SIMNET also generates VTU files that you can visualize in ParaView. And everything is built so that you can run it on GPUs and multi-node and multi-GPU machines. So whatever your system is, you should be able to run SIMNET on and take advantage of, take maximal advantage of the server and system you have. So one of the key features of SIMNET is a fully parameterizable constructive solid geometry module. So using Boolean operations, you can use object primitives like the torus or rectangle and things like that to construct your geometry. It's fully parameterizable, so any quantity in it you can parameterize and give a range over. So here's an example of a 3-fin heatsink that we've constructed where we parameterize the fin length and heights in different ways. And we solve the steady state flow over this heatsink with the conjugate heat transfer problem as well. SIMNET also contains a tessellated geometry module that allows you to work with complicated geometries defined as STL files. So here we have an example where we're solving the steady state flow in this aneurysm. In this library is accelerated with ray tracing methods that are very efficient for generating some of the needed point clouds for training and things like that. We use SymPy to describe the differential equations in SIMNET. And so this lets you actually symbolically write out the equations and boundary conditions that you're trying to solve for. Here's an example where we write out the Poisson equation. This is a very simple example, but when we start working with much more complicated things like turbulence models and things like that, this can be extremely helpful. SIMNET contains a model zoo of different neural network architectures to choose from. So there's a lot of literature right now on different neural networks you can choose. We've implemented a lot of the ones in the literature, as well as a few in-house networks that we've developed. Some of them can give substantial speed improvements in convergence of your problem. So SIMNET allows users to write out integral equations. Many partial differential equations of interest have integral formulations. There can be benefits to writing loss terms in these integral formulations instead of the differentiable ones. So for example, here we have the continuity equation for a velocity field. We can write it out as an integral equation here over a closed surface. And so what we can do is we can construct the loss function using this integral form, and then we approximate it with Monte Carlo integration, and we can do this in SIMNET. For some problems we have in the user guide with these heat sinks that we're solving and other Navier-Stokes type problems, we found substantially better convergence if we add in loss terms reflecting these integral formulations of the equations. So that is a feature that we have in SIMNET. SIMNET allows users to vary the loss weighting spatially. So one area of considerable interest is how to weight the losses with respect to one another. So if we're writing our loss as the sum of different components from boundary conditions and equations, if you weight the losses differently, it can have substantially different impacts on the convergence of the solver. So this is still a very open area and a very open research area that people are looking into. One idea that we have used to extend this is actually varying this weighting spatially. So we have this lambda for the residual, and we're actually going to vary it as if we're going to make it a function of x. And so we can do this in SIMNET, and we found that for some of our problems, specifically some of the Navier-Stokes problems that we're solving, this can have substantially this can provide substantially better convergence for our solver. All right, so that's all I'm going to talk about for some of the key features of SIMNET.
You can definitely download SIMNET from developer.nvidia.com/SIMNET. Again, developer.nvidia.com/SIMNET. There is a registration process. You will have to agree to click through the EULA, the user agreement, and then you can download. Please be sure to register with your organizational email, whether it's a university or a company, and not your personal email. Hopefully you can download SIMNET. If there are any questions, you can send your questions to simnet-team@nvidia.com, which is the email that you'll get for your queries. Any queries in the future you might have, we'll be happy to communicate with you and work with you if you decide to use SIMNET and work with that